The hydrogen energy market is expected to grow steadily. For example, in the past, it was estimated that the global hydrogen market would expand significantly within a few years, increasing in value by billions of dollars. This growth is not just driven by economic opportunity, but also by the fact that hydrogen has some clear advantages over other fuels. It contains more energy per gram than many traditional fuels, and when hydrogen is burned or used in fuel cells, it does not release harmful greenhouse gases. This makes it especially attractive to countries and companies trying to reduce their environmental impact. However, using hydrogen as a mainstream energy source isn't without its challenges. One of the biggest problems is how to store and move hydrogen safely and efficiently. Hydrogen is extremely light and takes up a lot of space unless it is compressed or cooled to extremely low temperatures, which requires special equipment and a lot of energy. Even when it's cooled, hydrogen doesn't easily become a liquid like other gases. Its low density means that storing a large amount of hydrogen in a small space is difficult, making transportation costly and complex. Because of this, the infrastructure required to handle hydrogen pipes, tanks, and other systems can be much more expensive than what's needed for traditional fuels. So far, hydrogen storage and transport have mostly worked well in small or specialized systems. But for hydrogen to be used on a much larger scale, such as powering entire communities or fueling fleets of vehicles, new solutions are needed. This includes creating infrastructure from scratch, as most existing pipelines used for natural gas cannot safely carry hydrogen. The main reason is a problem called hydrogen embrittlement, where hydrogen can weaken the materials used in regular gas pipelines, leading to cracks or failures. This means that using what we already have for natural gas simply won't work for hydrogen. That is why there is a strong push to invent new materials and technologies that can safely store and transport hydrogen over long distances. Around the world, many researchers and organizations are working on this issue. For instance, a typical utility company is one of many players exploring ways to modernize the energy grid to include hydrogen-based systems. Since the early 2010s, international groups like the International Agency of Energy have supported programs focused on hydrogen research. These programs are trying to find better materials and storage techniques that are both efficient and safe. Some of the promising areas of research include using porous materials that can trap hydrogen within tiny holes, as well as developing substances called liquid organic hydrogen carriers, LOHCs. LOHCs are chemicals that can absorb and release hydrogen under certain conditions, making them a safer and more practical way to move hydrogen. Other research is focused on different types of solid hydrogen storage systems, such as complex metal hydrides or intermetallic compounds. Scientists are also looking into better methods of electrochemical and thermal storage, which involve storing energy using chemical or heat processes. The hope is that, with continued effort and investment, the world will develop a reliable and cost-effective system to store and transport hydrogen. This will allow hydrogen to play a bigger role in our everyday energy use, helping to reduce pollution, fight climate change, and create a more sustainable future. As this technology continues to improve, it will be important for governments, companies, and utility providers to work together and build the infrastructure needed to support a global hydrogen economy. One of the most exciting and practical ways to store and move hydrogen is through something called liquid organic hydrogen carriers, or LOHCs for short. These are special types of liquids usually made from stable organic compounds that can safely hold hydrogen by bonding with it chemically. Some examples of these compounds include things like biphenyl, diphenylmethane, carbazoles, and indoles. Even though those names sound complex, what's important to know is that these materials stay stable in a variety of conditions, making them reliable for use in real-world situations. LOHCs can absorb hydrogen gas when they are exposed to specific conditions. This process turns them into a slightly different version of themselves, one that now carries the hydrogen safely inside. In fact, these liquids can carry quite a bit of hydrogen, up to 7.2% of their own weight. Once they're loaded with hydrogen, they can be stored in tanks or moved using trucks, pipelines, or tankers, the same systems already used today for transporting gasoline or diesel fuel. This means that we don't need to build an entirely new infrastructure to use LOHCs, which saves a lot of time and money. When it's time to use the hydrogen, the LOHC can be heated to a temperature between 180 and 240 degrees Celsius. A catalyst, basically a special material that speeds up chemical reactions, is used to help with this step. The hydrogen is then released from the LOHC and can be used to power fuel cells, generate electricity, or support industrial processes. After the hydrogen has been removed, the liquid carrier isn't thrown away. Instead, it gets sent back to the location where hydrogen is added again, and the cycle starts over. This recycling process makes LOHCs more cost-effective over time. LOHCs are especially useful when we're talking about hydrogen made from renewable energy sources like wind and solar power. These energy sources don't always produce electricity at a constant rate, but that electricity can be used to create hydrogen through electrolysis. LOHCs can then be used to store that hydrogen until it's needed somewhere else. This makes LOHCs a great tool for helping renewable energy reach more places and be available when it is needed most. Compared to other hydrogen carriers like methanol, ethanol, or ammonia, LOHCs have several clear advantages. They are safer to handle, don't evaporate easily, and don't require high pressures or extremely cold temperatures. Plus, the best LOHCs are liquids at room temperature, just like diesel or gasoline, which means they're easy to pump, store, and transport. This makes LOHCs a very practical choice for moving hydrogen long distances without the need for high-tech or expensive equipment. The idea of using special liquids to store and move hydrogen, called liquid organic hydrogen carriers, or LOHCs, has actually been around for quite a while. Researchers first started exploring this technology back in the early 1980s. One of the earliest and most widely studied systems was based on two common chemicals, toluene and methylcyclohexane. These two could switch back and forth between forms by adding or removing hydrogen, which made them a useful pair for storing hydrogen in liquid form. Over time, scientists around the world began to study other chemical pairs that could work just as well or even better. In the early 2000s, researchers in Japan began looking closely at another combination, cyclohexane and benzene. Around the same time, other scientists proposed new types of LOHCs that involved nitrogen-based chemicals, which they believed might offer better performance. These ideas helped to expand the range of possible materials that could be used for storing hydrogen safely and efficiently. As interest in hydrogen as a clean energy source continued to grow, more and more researchers joined the effort. Some teams began to explore advanced materials like isoboron compounds, which showed promise for storing hydrogen in a compact and stable form. Others suggested that LOHCs containing nitrogen-based rings known as heterocyclic compounds might provide improved storage efficiency. These ideas were supported by scientific calculations and lab tests that showed how these materials might work in practice. A major step forward happened when Toyota Corporation, a company in Japan, built and successfully ran a pilot plant designed to test LOHC technology on a larger scale. This plant demonstrated that hydrogen could be added to and removed from LOHC materials reliably and in significant amounts. This was an important milestone because it showed that the technology wasn't just a laboratory idea, it could actually be used in the real world. Since then, researchers and engineers have been working on ways to make LOHC systems even more practical. They've explored how LOHCs could help store energy locally in small networks, how they could be used in power systems that generate both heat and electricity, and how they might support industrial energy needs. These developments show that LOHCs have real potential in many different areas, especially when paired with renewable energy sources like wind and solar. Today, LOHCs are being seen not just as a scientific curiosity, but as a serious solution for storing and transporting hydrogen. Their safety, flexibility, and ability to use existing fuel infrastructure make them especially attractive. Scientists continue to run experiments, create models, and use computer-based tools like density functional theory to better understand how LOHCs work and how to make them even more effective. One of the smartest ways scientists have come up with to store and move hydrogen involves something called energy-carrying compounds. These are special chemicals that can exist into different forms. One that is full of energy, we call this energy-rich, and one that has already given up its energy poor. This back and forth transformation forms the basis of what's called an LOHC system, short for liquid organic hydrogen carrier. Here's how it works in simple terms. At a location where there is plenty of energy like a solar or wind farm, hydrogen is created using electricity from those clean sources. That hydrogen is then added to a liquid organic compound in a process called hydrogenation. This charges the LOHC and makes it energy-rich. Once charged, the LOHC can be transported safely and stored for a long time without needing special tanks or extreme conditions. When the energy is needed somewhere else, like at a power plant or a fueling station, a process called dehydrogenation removes the hydrogen from the LOHC. That hydrogen can then be used in things like fuel cells or burned to produce electricity and heat. The empty LOHC, now in its energy-poor form, can be sent back to be recharged again. This cycle can repeat many times, making the whole process very efficient and environmentally friendly. One of the most exciting things about LOHCs is that they let us separate when and where we create energy from when and where we use it. For example, a typical utility company could produce hydrogen during the day when the sun is shining, store it in LOHCs, and deliver that energy to homes or businesses at night when the demand is higher. This flexibility is one of the key reasons experts around the world, scientists, engineers, and even politicians, see hydrogen as a strong option for clean energy transport. Hydrogen is a very light gas with a lot of energy packed into it. But storing large amounts of it has always been tricky. You either need to compress it under very high pressure or cool it to extremely low temperatures. Both of these options are expensive and require special equipment. LOHCs offer a much more practical solution because they allow hydrogen to be stored as a safe, stable liquid using systems similar to what we already use for gasoline or diesel. One specific example of an LOHC that has shown a lot of promise is called a methylcarbazole. This compound can hold up to about 5.8% of its weight in hydrogen when it is fully charged. To add hydrogen to this compound, scientists use a special catalyst often made of the metal ruthenium placed on aluminum oxide and heated to around 130 to 160 degrees Celsius under high pressure. When it's time to remove the hydrogen, a different catalyst, usually made from platinum or palladium, is used, and the temperature is raised to about 200 to 230 degrees Celsius under moderate pressure. What's great about this whole method is that it makes storing hydrogen much easier and safer. The liquid doesn't leak hydrogen into the air, and it's not flammable in its uncharged state, making it much easier to handle and transport. Thanks to these advantages, LOHCs offer high energy density and are becoming a very attractive choice for energy storage in the future. Many current hydrogen storage systems face challenges that limit their practical use. These challenges include storing low amounts of hydrogen by weight and volume, needing a lot of energy for storage and release, and slow reaction speeds. Because of this, scientists continue searching for better storage methods. One promising method is called liquid organic hydrogen carriers, or LOHCs. This idea started in the early 1980s LOHCs are special liquids that can absorb hydrogen and release it later while staying liquid both times. They have some clear advantages over other storage methods. For example, they can hold a lot of hydrogen in a small space and weight, and they fit well with the current systems used to transport fuels. This means they don't require big changes to existing infrastructure, which lowers risks and costs. Research on LOHCs has mostly been done in labs so far, and practical, large-scale systems are still being developed. The goal for LOHC developers is to find organic compounds that are cheap, easy to get, and able to hold and release hydrogen efficiently. Ideally, the same catalyst would help both at hydrogen hydrogenation and release hydrogen dehydrogenation under mild conditions, making the process more efficient. The process works by storing hydrogen through a reaction that happens under pressure and releases heat. When hydrogen is needed, it is taken out through a reaction at lower pressure that needs heat input. These systems can use pressures around 20 atmospheres for storage and about 5 atmospheres for release. A possible system design involves using hydrogen made from water electrolysis to add hydrogen to LOHC molecules. These hydrogen-rich molecules can be safely stored and transported using pipelines or regular fuel transport methods like trucks or ships. When the hydrogen is needed, it is released from the molecules to be used for energy. Because renewable energy sources like solar and wind change with the seasons, having a way to store hydrogen over longer times, like with LOHCs, is very helpful. Studies also show that using LOHCs to produce hydrogen for vehicles is cost-effective and better for the environment. LOHC systems use special liquid chemicals called aromatic compounds to store hydrogen. Early types of LOHCs included cyclic alkanes such as cyclohexane, methylcyclohexane, and decaline. These chemicals can release about 6% of their weight in hydrogen by turning into their aromatic forms at high temperatures, usually between 300 and 350 degrees Celsius. This reaction uses platinum catalysts to help the process. One popular example is the methylcyclohexane toluene cycle. This system can store 6.1% hydrogen by weight and about 47 kilograms of hydrogen per cubic meter by volume. It is reversible, meaning the hydrogen can be stored and released many times, and it works without producing harmful byproducts. Scientists are working to improve these systems by trying to lower the temperatures needed for releasing hydrogen, which can save energy. They also focus on finding better, cheaper catalysts to replace the expensive noble metals like platinum. Other promising LOHC chemicals being studied include benzyl toluene, dibenzyl toluene, borane-based amines, and methylcyclohexane. These alternatives might offer better performance or easier use in real-world settings. When using LOHCs like ethyl carbazole, the hydrogenation and dehydrogenation processes create several intermediate compounds with different hydrogen levels. The mix of these compounds depends on how long the reaction runs and which catalysts are used. Research on LOHCs based on dibenzyl toluene showed that under controlled conditions and with the right catalyst, high conversion rates are possible. For example, platinum catalysts on aluminum oxide reached up to 99% conversion in 5 hours at around 270 degrees Celsius, while ruthenium catalysts were less effective. Some researchers tested a method where both adding and removing hydrogen happen in the same reactor using the same catalyst. This setup improved efficiency. Optimal conditions were about 140 degrees Celsius for hydrogenation and 270 degrees Celsius for dehydrogenation. The system showed good stability over multiple cycles, maintaining about 85% hydrogen storage efficiency after 5 cycles. This kind of continuous operation is promising for practical use. Although some LOHC systems have lower hydrogen content by mass and volume compared to others, the methylcyclohexane toluene system stands out because of its industrial advantages, such as compatibility with current technology and easier handling. Some new materials have been explored recently to improve how much hydrogen can be stored and how easily it can be added and removed from these carriers. One promising compound is 2-methylindole, which can hold about 5.76% hydrogen by weight. This makes it a good candidate for LOHC systems because it can store and release hydrogen under moderate conditions, meaning it doesn't require extremely high temperatures or pressures. Another material called 12-dimethylindole can store a little less hydrogen, about 5.3% by weight, but it has the advantage of quickly absorbing and releasing hydrogen at mild temperatures. It also melts at a comfortable 55 degrees Celsius, making it easier to handle. The chemical reactions involved with this compound follow predictable patterns and can be efficiently catalyzed using palladium-based catalysts. Anethylindole is another interesting material studied for hydrogen storage. Both it and its hydrogenated forms stay liquid at room temperature, which is helpful for practical use. The process of adding and removing hydrogen with anethylindole occurs smoothly with the help of ruthenium and palladium catalysts under relatively low temperatures and pressures. These reactions happen in steps, transforming the molecule gradually while producing high-purity hydrogen during dehydrogenation. Because of these features, anethylindole shows strong potential as a reliable LOHC. Scientists have also examined other possible carrier materials like unphenylcarbazole, furfuryl alcohol, and diphenyl ether with aromatic groups. These substances have been studied to understand their energy requirements for storing and releasing hydrogen, as well as how stable they are during these processes. Understanding these thermodynamic properties is essential to choosing the best materials for future hydrogen storage solutions. An important aspect of LOHC systems is ensuring the hydrogen produced is very pure. Research has shown that when using certain carriers like perhydrodibenzional, it is possible to get extremely pure hydrogen, over 99.999% purity, with very low levels of contaminants like carbon monoxide. However, impurities such as water or oxygen can cause problems during the hydrogen release process, leading to unwanted byproducts like CO and CO2. Therefore, careful preparation and purification of the LOHC materials, as well as controlling impurities, are crucial for making LOHC-based hydrogen storage practical and effective for industry and applications such as fuel cells. LOHC systems can be grouped mainly into two categories based on their molecular structure: homocyclic compounds and heterocyclic compounds. Homocyclic compounds are molecules with rings made up only of carbon atoms, while heterocyclic compounds have rings containing other elements like nitrogen. Both types have shown promise for storing hydrogen safely and efficiently. Recent research has also worked on designing model catalysts that can better handle the hydrogen release process for these molecules. Among the homocyclic group, popular examples include toluene, naphthalene, and monobenzyl toluene. These have been studied a lot because of their stable properties and hydrogen storage capacity. On the other hand, in the heterocyclic group, compounds like phenazine, indole derivatives, and 2-1-methylbenzylpyridine have gained attention due to their interesting chemical behaviors and potential for hydrogen storage. Some related compounds, like NEC-derived molecules, are not covered here since other recent works have already reviewed them in detail. One of the earliest and most well-known systems used for storing and transporting hydrogen is based on the toluene and methylcyclohexane cycle, often called the TOL-MCH system. In this system, toluene is converted into methylcyclohexane, a liquid that can hold a significant amount of hydrogen, about 6.2% by weight under normal conditions. This meets the hydrogen storage targets needed for energy applications. The liquid form of methylcyclohexane is especially useful because it can be transported easily over long distances and used in many different ways. However, the process to remove hydrogen from methylcyclohexane, called dehydrogenation, requires very high temperatures and a lot of heat energy. This makes the process challenging. Platinum-based catalysts are the best known and most effective for this reaction. They work well, but have some downsides. For example, the catalysts can get clogged or poisoned by byproducts that stick to their surface, which means they lose effectiveness over time. They also require temperatures of at least 350 degrees Celsius to work properly, which can cause unwanted side reactions and the buildup of harmful residues called coke. Additionally, methyl cyclohexane itself has some practical challenges. It boils at about 101 degrees Celsius and has a low flash point of -3 degrees Celsius, which means it can evaporate or ignite easily, making handling and safety important considerations. Despite these difficulties, a Japanese company called Chiyoda Corporation has successfully developed large-scale applications using the TOL-MCH system, showing its potential for real-world use. To improve how well catalysts work in methyl cyclohexane dehydrogenation, researchers have explored two main strategies. One is using bimetallic catalysts, which combine platinum with another metal such as manganese or tin. These combinations often work better than platinum alone and can reduce costs by needing less platinum. The other strategy is to use special supporting materials for the catalysts, like certain metal oxides and perovskites, which help improve the catalyst's stability and performance. The decalin and naphthalene system, another important method for storing hydrogen using aromatic hydrocarbons. Decalin has a good hydrogen storage capacity, about 7.3% by weight, which is higher than some other systems. However, the product formed when hydrogen is released, called naphthalene, is solid at normal room temperatures because it melts at just 8 degrees Celsius. This solid form creates difficulties for practical use, especially for transportation and handling. Another challenge with this system is that releasing hydrogen from decalin requires a large amount of heat, making the process energy intensive. Also, once decalin turns into naphthalene, reversing the process is not easy, which limits how practical it is for repeated hydrogen storage and release cycles. Benzyl toluene is part of a promising group of hydrogen storage materials known as LOHCs, which stands for liquid organic hydrogen carriers. One important system in this category is the perhydrobenzyltone H1-BT and benzyl toluene HOBT cycle. This system can store about 6.2% hydrogen by weight, making it effective for energy storage and transport. H1-BT, which is already used as a type of heat transfer oil, has physical and chemical properties that make it well suited to function as a hydrogen carrier. One advantage of H1-BT is that it requires less energy to release hydrogen compared to some other carriers, like H1-DBT. However, it does have a lower boiling point of 270 degrees Celsius, which limits how much hydrogen it can release in liquid form. Despite this limitation, H1-BT is more attractive for storing energy at lower temperatures. It releases hydrogen faster when a platinum-based catalyst is used at around 270 degrees Celsius. During the hydrogen release and storage processes, it forms simpler intermediate compounds, which helps make the reactions more efficient. Also, at room temperature, both HOBT and H1-BT have much lower thickness or viscosity compared to other similar compounds like H1-DBT. This lower viscosity means they flow easier, which is helpful for practical uses, such as transportation or pumping in a typical utility company's hydrogen storage system. Research has shown that heterocyclic compounds, especially those containing nitrogen atoms, offer some clear benefits compared to traditional cyclic aromatic hydrocarbons used in liquid organic hydrogen carriers (LOHCs). These benefits include faster reaction rates, better energy efficiency, lower temperatures needed for releasing hydrogen, and the ability to reverse the hydrogen storage process easily. This makes nitrogen-based heterocyclic compounds very promising for practical hydrogen storage. However, not all heterocyclic compounds are ideal. For example, some like dibenzofuran and dibenzothiophene tend to produce unwanted byproducts during the hydrogen release process, which limits their use in LOHC systems. On the other hand, indole derivatives and compounds like carbazole have been studied extensively because of their more favorable properties for hydrogen storage. Other nitrogen-based compounds, such as phenazine and 2-methylbenzylpyridine, are also important players in the field. Indole and its related compounds show many promising features that make them good candidates for hydrogen storage using LOHC technology. These compounds are similar to carbazole derivatives and have several useful properties. For example, they melt at relatively low temperatures, which helps in handling and processing. They also require lower temperatures to release hydrogen, which makes the process more energy efficient. Additionally, they can store enough hydrogen to be useful for practical applications. Researchers have found that by adding alkyl groups to the pyridine rings of indole molecules, the amount of energy needed to store and release hydrogen can be lowered. This also slightly reduces how much hydrogen the molecules can store, but the trade-off can be beneficial. These modified indoles can be made safely and in ways that are better for the environment, which is important when considering large-scale use. There has been a lot of research focused on the hydrogenation, adding hydrogen and dehydrogenation, removing hydrogen reactions of various indole derivatives. Some of the key compounds studied include unmethylindole, unethylindole, 2-methylindole, and 12-dimethylindole, along with their fully hydrogenated forms. These studies show that these substances have strong potential as liquid organic hydrogen carriers because they can efficiently absorb and release hydrogen under conditions that are easier to manage compared to some other compounds. This makes them attractive for future hydrogen storage solutions that a typical utility company might consider adopting. In recent years, scientists have been studying a new type of compound called 2-unmethylbenzylpyridine, or MBP for short, as a potential liquid organic hydrogen carrier LOHC. This compound can store a good amount of hydrogen, about 6.15% by weight, and stays in liquid form under normal room conditions. This makes it very convenient for practical uses. Researchers also found that MBP is relatively easy to produce and, based on calculations, it can overcome some of the usual energy barriers that limit other hydrogen storage materials, which means it could be useful in real-world applications. When testing different catalysts to help with hydrogen storage and release, it was found that the catalyst Ru, aluminium oxide, works well for adding hydrogen to MBP hydrogenation, while PDC is better at helping release hydrogen from MBP dehydrogenation. MBP also has some practical advantages. It has a low viscosity, meaning it flows easily, which is better for transport and handling compared to other LOHCs like dibenzyl toluene or ethylene glycol. It also performs well in corrosion tests, which suggests it won't damage storage containers or pipes, making it safer and more durable for transportation and storage. In addition, MBP has shown good stability and consistent hydrogen storage performance over multiple cycles of use. This means it can be used repeatedly without losing effectiveness, which is important for any material meant for ongoing hydrogen storage and release. In hydrogen energy storage systems that use liquid organic hydrogen carriers, LOHCs, scientists have been working hard to find the right catalysts to make the process of storing and releasing hydrogen more efficient. A catalyst is a material that helps speed up a chemical reaction without being used up itself. In LOHC systems, catalysts are needed to help add hydrogen to a liquid hydrogenation and then remove it when needed dehydrogenation. Some of the most effective catalysts are based on platinum group metals. These metals like platinum PT, palladium PD, and ruthenium Ru are known for their excellent performance in reactions involving hydrogen. For example, platinum has been shown to work especially well in helping release hydrogen from certain chemical liquids like octahydroindole and methylcyclohexane. In experiments, platinum was able to carry out this reaction with high efficiency and without breaking down, making it a strong choice for practical use. However, these metals are expensive, so scientists are also developing catalysts that combine a small amount of a precious metal with a cheaper one called bimetallic catalysts. For instance, one successful example is a catalyst made from ruthenium and palladium RuPD supported on alumina alco. This combination helped both with storing and releasing hydrogen using a compound called unpropyl carbazole. Another example is a catalyst using palladium and copper PDQ placed on a special surface called reduced graphene oxide. This version performed very well and could be a strong alternative in future hydrogen systems. In other cases, cheaper metals like nickel are added to reduce costs and improve the overall reaction. One promising design mixed palladium and nickel on a silica base, which achieved full conversion of the storage liquid and maintained high hydrogen purity. This PD&I combination even outperformed the version that used only palladium, showing that smart combinations of metals can be more effective and less expensive. Some scientists are also experimenting with ways to improve catalysts by changing how they are activated. For instance, using microwave energy with certain materials like titanium dioxide (TiO) has shown to boost the performance of catalysts even further. The form of the TiO crystal, whether it is rutile or anatase, can make a big difference in how well the hydrogenation reaction works. Researchers have been testing different types of titanium-based support materials to find which ones work best in hydrogen storage systems. One commercial material called P25, which contains a mixture of two forms of titanium dioxide anatase and rutile, turned out to be one of the most effective. This makes it a strong candidate for use in systems where liquid organic hydrogen carriers, LOHCs, are used to store and release hydrogen. In another study focused on LOHC systems, scientists looked at how well different catalysts help remove hydrogen from a compound called perhydrobenzyonal. They found that using just 1% platinum on an aluminum oxide-based PT, aluminium oxide significantly improved the amount of hydrogen that could be removed. When the temperature was increased from around 290 degrees Celsius to 320 degrees Celsius, the amount of hydrogen released jumped from 40% to 90%. However, higher temperatures also caused more byproducts, which lowered the purity of the hydrogen. Using a slightly stronger catalyst with 2% platinum gave a higher result, up to 96% dehydrogenation. When different metals were tested, the results varied a lot. Palladium PD on its own or mixed with platinum didn't perform nearly as well. In fact, the palladium-only system only reached around 11% dehydrogenation. This means palladium is likely not a good fit for this particular hydrogen release process. The speed of the reaction followed what's called first-order kinetics, meaning it depends directly on the concentration of the substance being converted. The energy needed to get the reaction going was different for each catalyst. Platinum needed the most energy, while the platinum-palladium mix required the least. But lower energy doesn't always mean better results in this case. In a different experiment, a group of scientists tested a one-pot hydrogen storage method that involved methanol and a type of organic compound called 12-diamine. They used a special catalyst made from ruthenium, and it was able to both store and release hydrogen in a reversible way. This setup could potentially hold about 6.6% hydrogen by weight, which is quite efficient. Other types of metal complexes, especially those made with iron Fe and iridium ore, were also found to be good at handling reversible hydrogen reactions. These reactions usually produce or absorb hydrogen while converting alcohols into other useful chemicals. Some of the latest research has focused on using manganese and iron with what is called pincer-type ligands. These setups are not only good at releasing and taking in hydrogen, but are also practical for things like hydrogen storage systems and fuel cells. Finally, a material called LOHC, made from lanthanum and nickel, showed great promise in hydrogen systems based on unethyl carbazole. When the particles of LOHC were made very small, about 100 nanometers, they became even more effective and stable. This means they could be used in systems where hydrogen needs to be stored and reused multiple times without losing performance. In hydrogen energy systems, especially those involving liquid organic hydrogen carriers (LOHCs), catalysts play a vital role in storing and releasing hydrogen. The process involves two main steps: hydrogenation, where hydrogen is added to the LOHC molecule, and dehydrogenation, where hydrogen is removed. For these steps to happen efficiently, certain metals, especially those from the platinum group like platinum and palladium, are used as catalysts. These metals are often placed on support materials such as activated carbon, aluminum oxide alco, or silicon dioxide COs, which help hold and distribute the metal for better performance. Hydrogenation reactions are usually more efficient and can yield almost all the desired product, sometimes as high as 98%. However, the reverse reaction dehydrogenation is much more challenging. Getting a high hydrogen release rate is difficult under normal conditions because dehydrogenation catalysts often struggle to stay both active and stable over time. That's why scientists and engineers pay close attention to which base materials support the catalyst and how the catalyst is prepared in the first place. These details can make a big difference in how much hydrogen is released and how fast the reaction happens. In industrial setups, platinum or palladium-based catalysts are commonly used to remove hydrogen from aromatic compounds. Among the catalysts tested, platinum on activated carbon PT, and platinum on aluminum oxide PT, alco stood out as the most effective for removing hydrogen from a compound called perhydrodibenzional. When using PT, alco, over 95% of the compound could be converted in just 3.5 hours at around 290 degrees Celsius, and the fastest hydrogen production happened at about 310 degrees Celsius. While activated carbon is an affordable material for supporting catalysts, it doesn't hold up well mechanically. This has led researchers to explore other support materials like titanium oxide and lanthanum oxide. In particular, catalysts using titanium oxide as a support, especially a type called TOR, showed better performance than traditional supports like alco. In fact, TOR-supported platinum catalysts performed almost as well as those using activated carbon. Interestingly, the difference in performance among these catalysts wasn't due to the surface area or the size of the particles in the support material. Many different types of catalysts have been studied for their ability to release hydrogen from a compound called methyl cyclohexane. Scientists have experimented with platinum on materials like alumina and silica, and even used combinations of magnesium and cerium. They've also tested how different temperatures and molecular shapes affect how much hydrogen can be released. This has included studying compounds with ring-like structures, such as benzene and terpenols, that can absorb hydrogen and then later release it. These experiments have shown that catalysts like 5% platinum on silica are very effective, especially when heating the system to about 320 degrees Celsius. Another important area of study has been a material called mu, which has a sponge-like or mesoporous structure. When palladium is added to mu, the combination becomes very effective in absorbing and releasing hydrogen from molecules like an ethyl carbazole. One major benefit is that this system works at relatively low temperatures and shows much better performance than more traditional catalysts, like palladium on alumina. The added palladium helps break hydrogen molecules apart and increases the amount of hydrogen that can be held in the mu. One exciting development is a new type of catalyst made by combining ruthenium and palladium on alumina. This blend works especially well in both storing and releasing hydrogen using unpropyl carbazole. What's impressive is that it remains stable even after 3 full storage release cycles, making it a strong candidate for long-term use in real industrial hydrogen storage systems. Researchers are also making great progress with metal complex catalysts that have something called pincer ligands. These are special chemical structures that make the catalyst more efficient. For example, a soluble ruthenium-based catalyst has shown a hydrogen storage capacity of about 6.5%, which is considered very high. Even better, this system can be recharged, meaning it can be used again and again. Pincer ligands have also made it possible to use cheaper metals like iron and manganese, which were once considered too weak for this job. This helps reduce costs without losing performance. In Japan, a company called Toyota has built a hydrogen storage system using a chemical pyrrolidine and methyl cyclohexane as its LOHC. They use a platinum-based catalyst with added sulfur to improve its performance. This catalyst has been tested in labs for thousands of hours and has maintained a high conversion rate and excellent product purity. The sulfur helps by protecting the platinum from breaking down the fuel molecule too much, which increases both the life and effectiveness of the catalyst. Finally, researchers in Russia have explored using new materials like glass fabrics to support platinum and palladium catalysts. These supports help control how the catalyst reacts with gases and liquids. This allows for continuous hydrogenation, where hydrogen is added smoothly over time. These systems work under relatively gentle conditions, which is important for keeping costs down and making the technology safer and more reliable. Hydrogenation happens when hydrogen molecules are added to the LOHC. This is a chemical reaction that gives off heat and typically occurs at moderate temperatures, around 100 to 250 degrees Celsius, and high pressure, about 5 to 7 megapascals. On the other hand, dehydrogenation is the process where hydrogen is released from the LOHC, and it requires energy input. Some catalysts can handle both hydrogenation and dehydrogenation, but the types of chemical bonds involved like carbon-oxygen, carbon-nitrogen, hydrogen-hydrogen, and carbon-hydrogen bonds mean that the reaction rates and requirements are different. So scientists have to be very careful when designing catalysts, often customizing them for specific LOHC systems. That means a catalyst that works well with one LOHC might not perform the same with another. A big part of the problem is the cost of the metals used in these catalysts. Some of the most effective ones contain rare and expensive metals like platinum, palladium, and ruthenium. These noble metals are great at what they do, but aren't easy to scale up for wide use, especially in large commercial energy systems. To get around this, researchers have started looking at alternatives using more common and cheaper metals like iron and nickel. Iron and nickel-based catalysts are more affordable and available, and some of them have shown good potential in lab tests. But there's a trade-off. These cheaper catalysts usually don't perform as well as the noble metal ones. They may not last as long, might not be as efficient, or may not target the right chemical bonds as precisely. To fix this, scientists are coming up with creative solutions like combining two metals to make bimetallic catalysts, changing the materials used to support the catalyst particles, or fine-tuning how the reactions are run. Another exciting area of development is in using advanced materials like metal organic frameworks (MOFs). MOFs have very high surface areas and can be designed with pores of specific sizes, which makes them a strong candidate for supporting catalyst materials. Their durability and customizability are appealing for use in LOHC systems. When it comes to improving the way catalysts work in liquid organic hydrogen carriers LOHC systems, the material that supports the catalyst plays a very important role. Researchers have looked into using non-oxide materials like carbon-based supports because they offer some benefits. For example, carbon nanofibers have been tested as a support for palladium catalyst during the dehydrogenation of perhydrocarbazole. This setup achieved a high conversion rate at relatively mild temperature and pressure conditions. Similarly, carbon nanotubes have been used to support platinum catalysts for dehydrogenating perhydrodibenzional with good conversion rates even at atmospheric pressure. These examples show that carbon supports can be very effective. Besides the choice of support material, adding promoters to catalysts has also been shown to improve their performance. For instance, adding bismuth to a platinum catalyst supported on carbon helped increase both the activity and stability during perhydrocarbazole dehydrogenation. Other elements like tin and zinc have been explored as promoters as well, showing promising effects. This tells us that both the support material and the promoters can greatly influence how well the catalyst works. The surface features of the support, including its pore size, chemical properties and how it interacts with the catalyst metal can affect the catalyst's overall ability to work effectively. Some newer catalysts, such as those combining palladium with special supports like aluminum oxide mixed with yttrium hydride or reduced graphene oxide, have shown promising results. These catalysts work efficiently at lower temperatures and with less use of expensive noble metals. For example, palladium nanoparticles spread on a metal organic framework called MIL-101 showed better performance than traditional commercial catalysts in hydrogen release reactions. Other research has compared catalysts made from different metals for specific LOHC systems and found that platinum supported on titanium dioxide tends to be especially effective. The interaction between platinum and titanium dioxide helps create active sites where hydrogen can be released more easily. At a certain platinum concentration, this catalyst released a high amount of hydrogen at a relatively low temperature, making it very efficient. Some studies also suggest that the dehydrogenation reaction depends on how the catalyst's structure interacts with the support. Strong connections between platinum and titanium dioxide appear to speed up the overall reaction. Research has also shown that palladium and ruthenium catalysts supported on mesoporous molybdenum oxide perform better than similar catalysts on aluminum oxide supports. Researchers are actively working on improving the catalysts used in hydrogen storage and release for LOHC systems. One significant development involved modifying platinum on aluminum oxide PT, aluminium oxide catalysts, by adding sulfur. This change helps the sulfur attach to specific spots on the platinum catalyst that normally cause unwanted side reactions. By blocking these spots, the catalyst works better and more selectively, meaning it focuses on the desired chemical reactions more effectively. The success of an LOHC system depends on two main things: how much hydrogen it can store and how stable it remains after many charging and discharging cycles. To give an example, a study tested the complete hydrogenation of dibenzyl toluene using a commercial nickel catalyst with 50% nickel content. Impressively, this was done at a lower pressure than usual, showing that it's possible to achieve good results under milder conditions. For the dehydrogenation step, they used a platinum catalyst on aluminum oxide to release hydrogen from perhydrodibenzyonyl. The study focused on how many times the LOHC molecule could be cycled before breaking down and how many byproducts formed with each cycle. Tests were done under tough conditions to see how durable the system really was. One interesting finding was about methane gas production, which increased in a specific order depending on the compound. Overall, the LOHC system using dibenzyl toluene showed strong performance. Even in harsh conditions, the amount of unwanted byproducts stayed low, around 7%, which indicates that this LOHC setup is quite robust and reliable for repeated hydrogen storage and release cycles. When it comes to storing hydrogen using liquid organic hydrogen carriers (LOHCs), reactors play a crucial role. Typically, the reactors used for hydrogenation, adding hydrogen, and dehydrogenation, releasing hydrogen work well for most LOHC systems. However, to get the best performance and improve overall energy efficiency, new and innovative reactor designs may sometimes be needed. One interesting approach is to combine both hydrogenation and dehydrogenation in the same reactor using the same catalyst. This means hydrogen can be added and released in one system, which simplifies the process and can make hydrogen storage more efficient. For example, platinum supported on aluminum oxide PT, aluminium oxide is commonly used as a catalyst in reactors for both adding hydrogen to dibenzyl toluene and releasing hydrogen from its hydrogenated form. This process works well within a certain temperature range, typically around 290 to 310 degrees Celsius. Researchers have also designed advanced reactors with multiple stages that improve heat and mass transfer during hydrogenation and dehydrogenation. These reactors include tiny structures that allow hydrogen to be separated from the reaction mixture it is formed using special membranes made of palladium and silver. This helps make the process faster and more efficient. In other studies, different catalysts like nickel molybdenum on aluminum oxide NEMO, aluminium oxide have been used for hydrogenating other promising LOHC materials, such as phenanthrene. These reactions happen at higher temperatures, and conversions of over 70% have been achieved, showing strong potential for these catalysts in hydrogen storage applications. There are also efforts to combine dehydrogenation reactors directly with fuel cell systems. For instance, when hydrogen is released from dibenzyl toluene, it can be fed straight into low-temperature fuel cells. To ensure the hydrogen is clean, activated carbon is used to remove impurities. Although small amounts of methane may still be present after purification, the fuel cells continue to work efficiently without losing power. Adding pure hydrogen can restore full power if needed. This shows that hydrogen storage reactors and fuel cells can work well together, and activated carbon is a practical, cost-effective option for cleaning hydrogen from LOHC systems. Finally, using membrane reactors where hydrogen can pass through special membranes directly during dehydrogenation is a promising technique. These reactors can improve efficiency and allow the process to run at lower temperatures, making the whole system more energy-friendly. Researchers have studied both the technical and economic aspects of liquid organic hydrogen carrier LOHC storage systems to understand how practical and cost-effective they are. For example, some investigations have looked at how LOHCs could be used in vehicles and how much it would cost to store useful amounts of hydrogen, around 5.6 kilograms, in liquid organic forms. These studies often use mathematical models to predict how LOHC systems would work in real industrial settings, such as stationary energy storage plants operated by a typical utility company. One practical test by a major car manufacturer showed that using LOHC technology to store excess energy works well, but converting extra energy into heat was even more cost-effective in their setup. The LOHC system itself showed good energy efficiency, recycling about 69% of the energy during active use, and nearly 89% when not actively in use. These numbers highlight that LOHC systems can be reliable, but their efficiency depends on the specific conditions and use cases. Other studies have compared LOHC systems to alternative methods like transporting hydrogen as a liquid. These comparisons take into account the entire life cycle of the storage system, including environmental impact, natural resource use, health factors, and the capital and operating costs involved over the system's lifespan. The results indicate that no one method is perfect. For instance, although transporting liquid hydrogen can be expensive, LOHC systems demand a lot of heat during the hydrogen release process and have lower transport capacity, which can make them less environmentally friendly in some cases. When looking at the big picture of storing hydrogen on a large scale, methods like liquefied hydrogen are common. However, chemical bonding methods such as methanol, ammonia, and LOHCs show potential to compete, especially regarding energy needs during storage. These chemical storage methods require more heat to release hydrogen, but this heat can be supplied in different ways, like burning the LOHC material itself using a separate fuel source or using some of the hydrogen released during the process. Using liquid organic hydrogen carriers, or LOHCs, as flexible energy carriers is an exciting idea that could help build a greener and more sustainable energy system in the future. However, the chemical processes and technology needed to make this work are still in the early stages of development. To successfully put such an energy system into practice, there are several important issues we need to address. One example of a LOHC is a methylcarbazole, which meets many of the basic requirements and serves as a useful test material to explore how LOHC systems might function. Despite its advantages, it is not perfect. For instance, pure unethylcarbazole is solid at normal temperatures, which can be a problem. To solve this, technical methods like mixing it with other substances or partially removing hydrogen may be necessary, but these fixes might also reduce how much hydrogen the system can store. Before choosing any substances for LOHC systems, it's crucial to study their toxicity and environmental impact carefully. Even though hydrocarbon-based fuels are generally harmful, using LOHCs on a large scale could produce a lot of waste. So understanding the health and environmental effects is very important. The ideal LOHC would balance how much hydrogen it can hold, how toxic it is, and how much it costs. While hydrogenating aromatic hydrocarbons is a well-known industrial process, creating effective devices to remove hydrogen onboard vehicles is a newer challenge. Cars and other vehicles have very strict needs for these devices. They must produce high power and quickly adjust to changing conditions. Another big factor affecting costs is how much precious metal, like platinum, is needed in the catalyst to generate hydrogen. In some vehicles with internal combustion engines, waste heat can power the hydrogen release process from the LOHC. But this method won't work well in fuel cell vehicles because fuel cells don't generate enough heat. Fuel cells also need very pure hydrogen to avoid damage, so developing ways to connect fuel cells with LOHC storage safely and efficiently is essential for future clean transportation. Finally, there is some hope that existing fossil fuel infrastructure like pipelines and storage facilities could be adapted to distribute LOHCs. However, we still need detailed studies to understand what changes would be required and how much those changes would cost before this can become a reality. Overall, while LOHC technology shows great promise, more research and development are needed to overcome these challenges and make it practical on a large scale.